In our project, we implemented a concurrent lazy segment tree. Lazy segment tree is a data structure that supports fast range queries, and with lazy propagation, it also optimizes range update operation by delaying the propagation caused by an update until it becomes necessary to do so. In our work, we try to further optimize the performance of lazy segment tree by first trying to parallelize the individual operations and then attempting to make the data structures thread safe so that it supports concurrent read in a single writer, multiple reader workload model. After implementing the sequential version of the data structure, we noticed two potential possibilities of parallelism, which are in the push and build helper functions. All the other functions have this parent and child dependency that are inherently can be only executed in a sequential manner. Uh, so we implemented our parallelism using both ISPC and OpenMP, which corresponds to a SIMD and a multi-core approach. And we ran multiple experiments on the Gates machine and the Bridge machine, but we um, noticed no speed up on both Gates and Bridge machines, as we can see from the generated graph. Uh, this result was unexpected, but it makes sense after we took a closer look at the code. Since we originally designed push and build functions to operate on arbitrary range, but in the actual implementation, push and build are only called on range that are equal to 1, which means the inner for loop, um, the for loop we are trying to parallelize here, will only ever loop for one iteration in our implementation, which is why parallelism using both SIMD and multi-core didn't help at all. Uh, After the unsuccessful attempt of parallelizing the individual operations, we shifted our focus onto implementing concurrency in the single writer, multiple reader model. Uh, the technique we used here is fine-grained locking. Uh, Specifically, instead of locking the entire tree on every operation, we used a read-write lock that's supported in the pthread library, in which either one writer can acquire an exclusive lock, or many readers can acquire a shared lock. With this type of lock, we could support concurrent readers at the same time as opposed to the coerce-grained approach that only supports one reader at a time. And the benchmark program we run our implementation against is um, a thread simulation of a single writer, multiple reader workload. And we ran the experiment on the Bridge machine. And the result of our experiment looks promising, as we can see from the generated graph here. When running the workload on Bridge machine, we noticed a good amount of decrease in execution time using fine-grained lock compared to using coarse-grained lock. Because in the single writer multiple reader workflow model, reading, namely calling the range sum, is more frequent than updating the data structure. So with the read write lock and the fine-grained lock implementation, um, it shows a better performance comparing to uh, a coarse grained lock.